Hello everyone. So welcome to the this 8th tutorial session of Probability Foundation of Electrical Engineers, and whose instructor is Professor Krishna Jagannathan sir from IIT Madras, and I am Satyavikram Pratap Singh, a PMRF research scholar at Department of Energy Science Engineering, IIT Bombay. So we have seen few of the problem in the last session, which have helped you to solve the assignment 8 basically, starting from assignment 0 and 1, 2, 3, 4 to 8, and then we are moving forward with the problems which will help to solve the assignment 9, 8 and 9. Okay, so moving forward, so this is the first problem before you. So here it is asking that for non-negative measurable Fn on omega f mu, which inequality is Fato's lemma. Okay, just you have to tell me that which actually inequality is the Fato's lemma, which is options are actually matching with that. Okay, if you face any doubt, just let me know. Okay, let me give you a solution for this. So when you see that this omega f and mu is a measure space and fn is a non-negative measurable. Okay, so what is a Feto's lemma? It says that when you integrate with respect to in the region of omega, and the limit is till n tends to infinity, that is f and d mu, and when you take the limit out, which it should be greater or equal to limit infinite and tends to infinity in the area of omega fn du mu. Okay, so when you build in and increase the sequence from the fn for each k belonging to the n, it defined as sk omega is equal to in inf of fn omega n greater equal to k. Okay, so then sk is increasing in k, because you have to take the infimium over a small trial of k which grows, and so that the limit sk omega will be limit s tend to infinity inf fn omega for every omega. Okay, so when you apply the monotone convergence theorem, that is MCT theorem, since the Sk is growing, Sk is increasing, and limit in INF of Fn and each Sk is greater equal to 0. Okay, so when you take the limit, integrate it, limit INF Fn and it in the n. So when you take the limit k tends to infinity integral of Sk. Okay. Similarly, when you compare the infinity of integral of Sk to, not like this integral of sk to integral of fn, when you compare it, the integral of sk is less than equal to integral of fn for all n greater than equal to k. Okay, so integral of sk is less than equal to infinity n greater than k and integral of fn. Okay, take the limit on the both side and combine the step 2 and 3. What is step 2? Step 2 is basically the applying the MCT theorem, and step 3 is comparing the integral of sk with the integral of fn. Let's compare it. When you take the combine it, so it will become limit inf of fn is equal to limit k tends to infinity integral of sk less than equal to limit inf integral of fn k tends to infinity and greater equal to k, and it is equal to limit inf and tends to infinity integral of fn. So when you say that option B is actually matching, because integral of limit of inf fn is less than or equal to limit of inf integral of fn. Okay, so that's why the B option is actually correct. Okay, why the option A is not correct? Because it's already coming out now. Okay, integral of when you take fn, that is taking the integral out, this is not, is a generalized way. Okay, so inequality direction goes the other way also, that is not the bounded situation. So when you take the extra under extra upper bounds assumption, so it's a reverse pattern. Okay, so that's why the option B is actually matching. Okay, let's move forward, try to solve this problem. Okay, let me give the solution for this. In this question, it is asking which set of hypotheses is sufficient for when you take the integral fn tends to integral of f. Okay, when you say we want that integral of fn tends to integral of f. Okay, so fn tends to f. Let's assume that it's a almost everywhere. Okay, when you take the mod of fn less than or equal to g for some integrable g belonging to L inverse of mu. Okay, so then fn minus f mod is less than or equal to mod of fn plus f, and this is similarly when you take it fn less than or equal to g, put it there. So when you kept it g plus g, okay, 2g. So it means that mod of fn minus f is less than or equal to mod of fn plus mod of f less than or equal to g plus g equal to 2g. Okay, so and f is integrable by mod of f less than or equal to g. Okay, since fn tends to f, so we have fn minus f tends to 0 and fn minus f less than or equal to 2g. Okay, when you integrate it, it will become simply mod of fn minus mod of f, integral of fn minus integral of f, which is less than or equal to integral of mod of fn minus 1, which is tending to 0. So it means that integral of fn is tending to integral of f. Okay, so when you say that why the other options are actually not matching, so option C is actually correct. When mod of fn is less than or equal to g with g belonging to L1. Okay, why the other option not sufficient with the q counter examples like fn is tending to f, that is fn greater equal to 0, not enough without monotonicity. Okay, the counter example should be such that when you take the r leb, so let fn is equal to 1 inside of the n plus 1, so then fn is greater equal to 0 and fn is tending to 0, but here it is not actually matching with that. Okay, or even you say that fn tends to f uniformly, not enough on the general measuring bell space. Okay, and fn tends to fn is a probability only, not enough. Okay, when the counter example will be such that fn is tending to 0 in a probability, but integral of fn is equal to 1, and which is not tending to 0 is equal to integral of 0. Okay, so let's move forward, try to solve this problem. Okay, let me give the solution for this. In problem, when you see that it is asking if fn is greater or equal to 0 and integral of g is less than infinity and with fn greater or equal to g, which is always option is true. Okay. So when you see the Feto's lemma, so this is just simply the integral will be look like. So this is exactly matching with the option B. But the problem here is it is matching with the option B. But the problem here is when you see the stepwise, when you take the reverse Feto, use domination to flip the inequality for ellipse, and because fn is less or equal to g, so g is belonging to the L1, so g minus fn will be greater or equal to 0. Okay, apply Fato theorem. So here when you see the limit n infinity g minus fn less than or equal to limit n infinity integral g minus fn. Okay, pointwise limit infinity n g minus fn is equal to g minus lim sum of n fn. Hence, when you subtract it, take the integral. These are matching with the exactly the option B. Okay, so it is matching with the option B. Try to solve this problem. This is related to identity of the expectation of x. Okay, let me give the solution for this. When you see that what is asking for an integral x which identity link to the tail to the mean for x greater equal to 0. Okay, when you see that what is the expectation of x, is it simply the probability when you finding out that probability of x greater equal to x. Okay, for x is greater equal to 0 because it should be integrable. Okay, for each omega when you take the, suppose I'm taking a layer cake or ternary, so for any omega write the layer cake representation such that x omega is equal to 0 to infinity 1 dx and x omega is greater equal to x, because integral when you take it is equal to 1, so when you integrate it, it is simply become 0 to infinity probability of x greater than equal to x. So it is matching with probability of 0 to infinity probability of x greater than equal to x. Simply. Okay. So option A is correct. Let's move forward. Try to solve this problem. Okay, let me give the solution for this. When you say if expectation of x, what is given, is less than infinity, what will be the concluded about the x probability of mod of x greater than x as x is tending to infinity? Okay, when you say that, so let's f is a probability of mod of x greater or equal to 0 when then the f is non-increasing and 0 to infinity fx dx is equal to expectation of x less than infinity. Okay, tail mean identity basically. So when you fix the this epsilon greater than or equal to 0, choose m so that the m tends to infinity ft dt is less than epsilon. Possible since the integral is finite. Okay, for x greater than 2m, because f is non-increasing for all t belonging to x by 2 comma x, we have ft greater or equal to fx. Hence x by 2 fx less than or equal to x by 2 to x ft dt is less than or equal to integral of m tends to infinity ft dt less than epsilon. Okay, therefore x fx is less than 2 epsilon for all x greater than 2m. Okay, implying greater than x tends to infinity, tends to 0. Okay, so the option C is actually correct. Okay, let's move forward, try to solve this problem. Okay, let me give the solution for this. Let y is equal to expectation of x such that the z is already occurred, which is the standard identity. When you see that, so it is being said that this is the assumption that y is equal to expectation of x such that z is already occurred, then expectation of x minus y of whole square will be equal to expectation of x square minus 2 times of expectation of xy plus expectation of y of square. Okay, so use the tower property, that the fact that y is z measurable. Okay, expectation of xy is equal to expectation of xxy such that z is already defined, and expectation of y multiplied by expectation of x such that z is already occurred is equal to expectation of y square. So when you plug it back, so here plugging here, so this is simply expectation of y square, it will become expectation of x square minus expectation of y square. Simply option C. Okay, sorry, this is not C, because this is expectation of whole square, but the here is expectation x square. Okay, so option E is correct. Let's move forward, try to solve this problem. So here it is asking what is the which orthogonality property is true for y is equal to expectation of x such that z is already been occurred. Okay. So here when you see, so here expectation of x minus y fz is equal to 0 for all bounded up where the y is equal to expectation of x such that z is already occurred. So here you have to take some assumptions like h is equal to sigma out z. So y is equal to expectation of x such that the h is already occurred and any bounded of fz is h measurable. Okay. Use the tau property. When you put it, it is coming out to be 0. Since expectation of x is such that h is equal to y, so the similar fashion expectation of y such that h is being already occurred, that is equal to y. So what is the correct answer? Correct answer is option B. Okay, let's move forward, try to solve this problem. Okay, let me give the solution for this. When it is being asked that what is the if there is a random variable x and y which identity basically holds. Okay, covariance of x, expectation of y, so that x is occurred. So like that, the four options are there. Okay, so when you take that convergence of x, expectation, so correct option B. Let's prove that expectation of x multiply expectation of y such that x is already occurred minus expectation of x multiplied by expectation of y such that x is being occurred and take its expectation. Okay, when you simplify, it will come out to expectation of xy minus expectation of x multiplied by x and y, which is simply equal to covariance of xy. Okay, so correct option is B. Let's move forward, try to solve this problem. Okay, let me give the solution for this. So it is asking what is a can ey is equal to infinite, but expectation of y such that x is less than infinity. Helmut's surely. Okay. When you see that, no, because it is usually said that ki L1 setting condition expectation is defined only for the integral y. Okay, by the tower property, which gives us the expectation of, when you see it is expectation of y. So if expectation of y is equal to infinity, this forces this value also to go into infinity. And if the expectation, it's expectation finite, the statement b rules out that ki finiteness is the sense interior. So that is not true. So no, because it is already being equal to the expectation of y. Okay, try to solve this. Okay, let me give the solution for this. It is saying law of total variance is that which is the options are correct with respect to the law of total variance. Okay, so when you say that, let's assume that, let's prove that key variance of y is equal to this expectation plus variance. Okay, so when you take the m of x is equal to expectation of y such that x and r is equal to y minus mx. So it's a condition we are taking that it's a linear increasing. So y is equal to mx plus r with expectation of r such that x is there is equal to 0. Okay. So expectation of mx r is equal to expectation mx r such that x is equal to 0. That is orthogonality. Okay. So variance of y is equal to expectation of m plus r minus expectation of y of whole square is equal to expectation of r square plus expectation of m minus expectation of y of whole square. Okay. So why others are wrong? Misses that ki variance on the second term, and it's a just a variance of y is equal to expectation of y square minus expectation of y of whole square. Condition of y that instead of x, not the total variance identity is there. Okay. So when you take the other question here, it is asking with correlation. Rho is equal to correlation between x and y. So variance of y is equal to sigma of y of whole square. So which upper bound is actually satisfying the criteria? There are four options. Just let me know which option is actually correct. Okay, let me give the solution for this. So when you see, it is asking which options is actually upper bound is a standard. Okay. So when you take the last time in the previous problem, which you take it the this assumption sigma y square is equal to variance of y. So when you find it out, it is already being proved in the previous problem. So convergence of y comma x is equal to convergence of mx comma x with the orthogonality property. So by Cauchy-Schwarz theorem, so variance of mx is greater or equal to covariance of mx comma x square divided by variance. Okay. So it's simply equal to covariance of y comma x of whole square divided by sigma x of whole square is equal to rho square sigma y of whole square. Okay, because rho square is simply equal to covariance of y comma x of square divided by sigma x squared sigma y square, or you can say that rho, which is covariance matrix, is equal to covariance of y comma x divided by sigma x sigma y. When you put it here, so it is equal to sigma y of square minus variance of mx, which is less than equal to sigma y square minus rho square sigma y square. Take it common, 1 minus rho square sigma y square. Okay. So correct option when you see, it's option B. Okay. Let's move forward. Try to solve this problem. Okay, let me give the solution. So here in this question is said that there is a worker which arrives with a uniform probability of 0 to 4 hour after 6 a.m. So the task time was t such that y is equal to y, which is increasing with the exponential of lambda y and with lambda y. Okay, is equal to 1 divided by 5 minus y. So expectation of t such that y is equal to y equal to, when you take, it's a arrival time is uniform distribution. Okay, so lambda y is given as 1 upon 5 minus 5, because it's a reaching. You see here it's after 6 a.m. Okay, so mean of the exponential is actually equal to 1 upon lambda. This is already we know. So quick check that expectation of x is equal to 0 to infinity t lambda e to the power minus lambda t dt. When you keep it here, minus t e to the power minus lambda t 0 to infinity plus 0 to infinity e to the power minus lambda t dt. This term will become 0, because when you keep it here, that term lambda tends to infinite, this term will become 0, and when you put the 0, it will become already 0. Okay, so it is equal to 1 by lambda. So we already know lambda y is equal to 1 upon 5 minus y. So expectation is 1 upon lambda, and lambda is 1 upon expectation of x. When you keep it here, 1 upon lambda y, keep the value 1 upon 5 minus y is equal to 5 minus y. And since y belonging to 0 to 4 and 5 minus y is belonging to 1 to 5, the later the arrival, larger y, the shorter the expected time, task time. Okay, consistent with the rate, lambda y is equal to 1 upon 5 minus y. Okay, increasing as y increases. Okay, so y increases, so this value, when it increases, minus y it decreases, so this value will increase, so lambda y actually increases, so expectation will become 5 minus y basically. Okay, the correct answer is option A. Try to solve this problem. Okay, let me solve this problem. So what is saying that in the same setup, what was the man was there with moving with the probability of uniform distribution 0 to 4. So it is asking that unconditional expected task time ET it is being asked. So when you try to solve it, because we have already found the ET such that y is equal to y is equal to 5 minus y, and y we already know it's a uniform distribution 0 to 4. Okay, so ET is equal to expectation of T such that is equal to y. So it is simply equal to 5 minus y, because we know that it's actually equal to 5 minus y. So we're simply taking the expectation only. So 5 minus expectation of y, because it's a constant, so you can take it out. So y is in the uniform distribution in between 0 to 4. It is such that like this. Okay, 0 to 4 it's a uniform distribution of 1. So when you take wanted to find out the average, okay, it is simply equal to 0 to 4 by 2, that is 2. Or you can simply that et is equal to 5 minus y. What is y is actually equal to 2, this is simply equal to 3. Okay, so when you see what are the correct option actually, and 80 is equal to so a is actually also correct, that is 5 minus y, but it is also correct because it's equal to 1 upon 5 minus y as well. Okay, try to solve this problem. Okay, let me explain that. It is asking that task completion time was 6 a.m. So is it C is equal to y plus t. So it is asking which identity is always valid. Okay. When you take the expectation, C is equal to y plus d, take the expectation on both sides. So it's equal to e the expectation of y plus expectation of t. So expectation, see that is the tau property when you use it. So it is y b can fail. That is t is equal to y, c is equal to 2y. So that's why when you take the two twice of the expectation of y, it is simply equal to expectation of y plus y. Okay. So that's why the random million, not the constant. So that's why the option B is not correct. So option A and C is correct. Okay. Try to solve this problem. Okay, let me give the solution. What is saying that mixture coin is there given q is equal to mean of mu, variance of sigma square. Xi says that q is equal to Bernoulli's of q with the conditional independent, which option is true. It is expectation of xi is equal to mu or variance of xi mu 1 minus mu. Covariance of xi comma xj is equal to 0 for all I does not equal to j, or expectation of xi is equal to sigma square. Okay, let Q be the random bias with expectation of Q is equal to me and variance of Q is equal to sigma square. Given Q, the flips are conditional independent with xi such that Q is equal nearly equal to Bernoulli's of Q. Expectation of xi is equal to mu, that is true. A variance of this, so correct option is actually option A and option B. Okay, that's all for today's session, and there are few more problems are there. You should try, and we will discuss in the future. Means lectures. Okay, when you feel any doubt is there, so we will discuss that. Okay, thank you so much for joining.